Hi folks, Chris McClure here. Well, just got back from a weekend. Finally had a weekend off. Been working the last several weekends. So we're going to continue where we left off last Friday. Last Friday I recorded a lecture regarding estimating the population proportion, in which we, took a sample. And this is the sort of sample where we asked a question: do you support Smith for governor, yes or no? Or which color do you prefer, black or white? Or whatever your experiment was, in which each individual in your sample was one of two possible outcomes. It was a binary choice. And we took the number of what we considered a successes divided by the total sample size to get the proportion, p hat, which estimates the population proportion. And then we saw how to calculate a confidence interval. Now we're going to continue with that discussion, but this time the statistic is the mean. Otherwise, the concept is still the same. The calculation of the margin error will be a little bit different than what you saw for the proportion. Okay? All right, so moving along here, we're going to be seeing how we can use a sample mean to make an inference about the value of the corresponding population mean, meaning for the population that our sample came from. All right, some key ideas here. We should know that the sample mean x bar is the best point estimate of the population mean mu, because of the fact that x bar is an unbiased estimator of mu. Number two, we should learn how to use sample data to construct a confidence interval, just like we saw for the proportion. And we should develop the ability to determine the sample size necessary to estimate a population mean. So if you remember what we talked about in this context from the population proportion, we'll see that is a similar calculation for the mean. Moving along here. Requirements for us to use the procedure that we're going to is that we have to be sampling from a normally distributed population, or the sample size needs to...
warning is over. All clear. All clear. All clear.
is that the sample size needs to be greater than 30. So either we sample from a normally distributed population, or our sample size is greater than 30. Now, before we get started calculating the mean, well, we already know how to calculate the mean. We just need to calculate the error. Margin of error, E, is going to be where we take this t critical value. I'm going to show you here in a minute how to find it, times the standard deviation for the sample divided by the square root of the sample size. Now this t statistic here, this t critical value, has n minus 1 degrees of freedom. What is t? Well, just like z is a standard normal distribution, well, letter t is also a continuous distribution, but it actually is a whole family of distributions dependent on the number of degrees of freedom. Degree of freedom is going to be one less than the sample size that you get from the population. Here's how you calculate your t statistic, where you take the sample mean x bar minus the known or presumed sample mean divided by the sample, I'm sorry, mu is the population mean. So you take the sample mean minus the population mean, and then you divide by the sample standard deviation, which is S, over the square root of n. All right, so remember that x bar minus mu over S over square root of n. That's going to calculate your t-value. This t statistic is normally, it's distributed according to the t distribution. It's very similar to the normal distribution, but it's not quite the normal distribution. The student t, well, student is kind of a generic name. It's kind of like the pseudonym, actually, of the mathematician who came up with it. He was actually more of an amateur mathematician. He was actually employed as a chemist for the Guinness Beer Corporation a few hundred years ago. But anyway, we shall use the t-distribution from time to time in the upcoming lectures. So this is what the t-distribution is. I know it looks kind of weird. What is the degrees of freedom? Well, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. Because of the fact that we have x bar and s in our calculation for the t-value, that's why we have 1 minus, because when we specify x bar and then s, that, once you know the 1, then you know all, well, you know that, if you know the mean, and all you would need to do is come up with all but one of the data values in order to calculate S, or vice versa. All right, number of degrees of freedom typically is n minus 1 when we're referring to the t-distribution. When you see the letter DF, that means degrees of freedom. Here's the listing of the alphabet soup that we're going to be using. I don't mean to denigrate my lovely math, but here's the listing of the notation that we'll use. Mu, of course, is the population mean. X bar, sample mean. S is the sample standard deviation. N is the sample size. Capital E is the margin of error. And this t sub alpha over 2 is the critical t-value, separated an area of alpha over 2 in the right tail of the t-distribution, similar to our discussion for z sub alpha over 2 from last time. Once you figure out e, then you take x bar minus e and x bar plus e to get the left and right limits for your confidence interval. All right, remember your e, your margin of error, is calculated as your t critical value times s over square root of n. I'll show you here momentarily how to look up your t values when we do our example. So here's the procedure for constructing the confidence interval for mu. This is also in your textbook, folks. We are assuming, by the way, that sigma is not known. Whenever sigma is not known, that's when we use the t-distribution. When sigma is known, what is sigma, by the way? Sigma is the population standard deviation. When sigma is known, then we'll use the z distribution. But when sigma is not known, we use the t distribution. We will verify that the requirements are satisfied. All right, I already showed you on the second slide, I think, what those requirements were. We'll use n minus 1 degrees of freedom, and we will look up our t critical value. Calculate margin of error, and then take x bar minus e and x bar plus e to get the left and right limits for the confidence interval. Okay, and then use reasonable rounding rules for the numbers that are your left and right limits. Here's our example here. Now, a lot of people who take vitamins a lot take garlic because there's this idea I'm not going to say it's a myth, but at least it's a commonly held belief, though, that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic. Raw garlic, not the pill kind, but just raw garlic. That's pretty rough if you've ever chewed on a clove of raw garlic. That's pretty harsh. So they were given raw garlic over some time. Their cholesterol levels were measured before and after this raw garlic treatment. Don't know the details of this garlic treatment, but it's probably over a period of a couple months. So they consume raw garlic every day. Anyway, we're going to measure their LDL cholesterol before and after. And then we'll calculate, the difference between the before and after. That's what we mean by the changes. So each person has a change in their LDL cholesterol. So the average change, assuming that this is a decrease, there's a mean of 0.4 for these 49 subjects and a standard deviation of 21.0. So we have mean, which is x bar of 0.4, standard deviation s is 21.0. So we're going to use the sample size of 49 subjects, x bar of 0.4, s is equal to 21.0 to construct a 95% confidence interval estimate of the mean. Estimate of the mean net change in LDL cholesterol after the garlic treatment. And also we'll answer the question, what does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? So here's our calculation. First of all, let's check the requirements. Do we have a simple random sample? Yes. We were told so in the statement of the problem. And we have a large enough sample size. It's greater than 30. So we don't need to know what the distribution of the population is that we sampled from. Because of the fact that we want a 95% confidence interval, that means that our critical level is alpha, which is equal to 0.05. We're going to use degrees of freedom of 49 minus 1, which is 48. Now, I'm going to get out of this. I'm going to pull up a t-table. You'll see this t-table toward the front of your textbook as well as toward the rear. Look for table A-3. Now, I'm going to go down because of the fact that 48 degrees of freedom is closer to 50. We'll look down this left-hand column, which is the degrees of freedom column, and look for the number that's closest to 48, which is going to be 50 in this case, so we'll use 50. And look across here, which of these numbers do we use? Well, let's take a look here. Well, because of the fact we want area in 2 tails of 0.05, we will use this middle column. Otherwise, half of 0.05 is 0.025, which tells us also that we will use the middle column. If you look across the top row, area in 1 tail is 0.0225. So we will go down this middle column down to degrees of freedom 50, and we will use 2.009 as our T critical value. Okay, so we've got our T value 2.009, standard deviation of 21.0, and n equals 49. Now this sigma really should be S, and that's a typo here. But put your standard deviation 21.0 and n equals 49, and for n. So you're going to have 2.009 times 21.0 divided by square root of 49, which is 7, by the way. 21 divided by 7 is 3. 3 times 2.009 is 6.027. So we have our margin of error, which is 6.027. And now we're going to take our x bar, which is 0.4, and add and subtract 6.027 that you see here. Here's where we subtract it, here's where we add it. And we've got our interval that goes from negative 5.6 to 6.4. And how we interpret this confidence interval is that there's 95% chance that this interval contains the true population mean. And notice, by the way, it contains 0. So there's a very likely chance that because of the fact this interval contains 0, that this treatment is really ineffective. This suggests that garlic treatment did not affect the LDL cholesterol because the interval contains 0. Okay? Now, talking more generally about the t-distribution beyond just this sample. Number one is the t-distribution is different for different sample sizes. That's why we need to know the degrees of freedom so we could look up the appropriate t-critical value. Because it's going to be different for different sample sizes, aka distribution, or degrees of freedom, which is n-1. Number two, the student t-distribution has the same general symmetric bell shape as the standard normal distribution, but it reflects the greater variability that is expected with small samples. Number three, the student t-distribution has a mean of t equals 0, just like the standard normal distribution has a mean of z equals 0. Number four, standard deviation of the student t-distribution varies with the sample size and is greater than 1. But it gets closer and closer to 1 the larger and larger the sample size. Number 5, as the sample size n gets larger, the student t-distribution gets closer to the standard normal distribution. Not just normal, but standard normal distribution. And here are just some examples here. In the blue curve, we have the standard normal distribution. If we have a really small sample size, n equals 3, we then have, say, this yellow curve. But with a larger sample size, we've got the red curve, and notice it's a lot closer to the blue curve, which is the standard normal. And as the sample size becomes larger and larger, the t-distribution will get to be closer and closer to the blue standard normal distribution. And just like we discussed for the proportions, is that if you only know the upper and lower limits for your confidence interval, then you can calculate x bar by taking the average of the upper and lower limits. And if you want to get the margin of error, then you just take the difference, upper minus the lower confidence limits, and divide by 2. Because the width of that confidence interval is actually 2 times the margin of error. Now, if it so happens that you don't know your sample size, but you need to figure out what your sample size should be in order to get your confidence interval within a certain margin of error E, then this is the calculation that you'll do, where we're going to at least make an estimate or an assumption regarding the population standard deviation, which is sigma. And also we will use the z value that's associated with alpha and divide it by the stated margin of error, which will be a decimal, and then square that result, and then round up to get the next larger whole number in order to get our minimum sample size to achieve that required margin of error. Alright, so you'll have a chance to do an example when you get to the homework. Actually, you do a couple. Now, if we don't know sigma, after all, why should we? But, maybe you have a good estimate based on some previous work that other people have done. But if you have absolutely no idea, here's what you could do. You could use the range rule of thumb that says if you were to be looking at some previous sample, then you could take the range, which is the largest minus the smallest value from that sample, and divide by 4. And that's a good estimate for sigma. So that's one thing that you could do. Another thing that you could do is start the sample collection process without knowing sigma. And so you can use this estimate up here, and then, with maybe a smaller sample size, calculate the sample standard deviation S and use it in place of sigma. The estimated value of sigma can then be improved as more sample data are obtained, and the sample size can be refined accordingly. Or you can estimate the value of sigma by using the results of some other earlier study. So you might have to do a review of literature, for example. So here's an example. Assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points? So we're going to put 3 right here for the required E value, margin of error. We're going to have our 1.96, which is our Z value associated with our critical level of 0.05, which is same thing as saying 95% confidence. And then 15 is going to be an estimate from somewhere. So when you do this calculation, 1.96 times 15 divided by 3, and square that result, that equals 96.04. Round that up to 97. So that tells us if we were to go out and take a sample of size only 97, at least 97 statistics students, then we will be 95% confident that the sample mean is within 3 IQ points of the true population mu. Now the second part will go a little bit more quickly, because here we're going to assume that we do know the population standard deviation. Okay? Everything else is the same. Except notice that we're not using our t value. We're going to go back to using our z value. We're going to assume that the sample is a simple random sample. Okay? Population standard deviation sigma is known. And either or both of these conditions is satisfied. Either we've sampled from a normal distribution or sample size is greater than 30. And we will estimate mu with the confidence interval by taking x bar minus e and x bar plus e, where the margin of error e is equal to your z critical value times sigma over square root of n. Again, for this calculation, we are assuming that sigma is known. So this should look familiar to you. Folks, this is what you use for your margin of error when you're estimating x bar and thus mu. When you know the sample standard, when you know the population standard deviation, when you know sigma, When it's known, then you are going to use your Z critical value here and sigma there, sample size in. Otherwise, if you don't know the population standard deviation, you use your T critical value here and S there. Okay? So here's a quick example here. People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats, aircraft, elevators, and other such devices do not become dangerously overloaded. Using the means of, or the weights of men, using the weights of men from a simple random sample, we obtained these sample statistics for the sample. Sample size 40. The sample mean is 172.55 pounds. And based on some research that we've done in the past, or looking at other people's research, we're going to go with a known or previously estimated standard deviation, give my sigma is equal to 26 pounds. Okay? So we're going to pretty much go through the same steps that we've done for the previous problem. We're going to calculate the point estimate, confidence interval, and then we'll answer this question. What do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? All right, so first, the sample mean is, the best point estimate of the population mean. And that was 172.55 pounds. Calculate the confidence interval, we need the margin of error, which is going to be your Z value, 1.96, times sigma over square root of n, so that's 26 over square root of 40. We were given sigma back here. We're told to assume that sigma is equal to 26. Because of the fact that we're assuming that we know the standard deviation, that's why we're using the Z value and sigma here, divided by square root of 40. And that works out to be 8.057483.5. And then we could take our X bar value. Remember, X bar is 172.55. Subtract E and add E. And by the way, there should be a plus here, by the way. This is X bar plus E. And X bar minus E to the left. And then you round appropriately when you get your final answer. So this shows that the average weight of the population of men lies within this interval between 164.49 and 180.61. Meaning, and we got to be kind of nuanced in this interpretation, there's a 95% chance that this lower and upper limit for this confidence interval actually contains the true population mean of men's weight. Notice, by the way, that this figure 166.3, let me go back here, 166.3, lies within this confidence interval. So it's entirely possible that this estimate of the mean men's weight from 1960 could be the mean weight of men today because it's within our confidence interval. But a better point estimate of 172.55, which is, by the way, about, 6 pounds greater, means that the mean weight of men is now considerably greater than it was in 1960. So we should really update our design guidelines so we can save some lives. So a study like this, which is relatively small, could lead to a much larger test, which would be the basis for updating guidelines for constructing boats and elevators and airplanes, etc. So this flow chart, by the way, here is going to tell you, how do you construct your confidence interval for mu? And the first question is, do you know sigma? Or at least, is there a presumed value for sigma? If the answer is yes, then use that z margin of error. If it's less than 30, then you have to use some other methods, non-parametric or bootstrapping methods, which, if this were a longer course, you would get to see. But because of the fact that, for the examples that you're going to do has a sample size greater than 30, you'll use that normal distribution, Z, calculation for the margin of error. But if sigma is not known, then you'll have to use the t distribution. Again, presuming that your sample size is greater than 30. Okay. Again, use your t distribution when sigma is not known. Use the z distribution when sigma is known. Okay, so that's it for now. By the way, there's a handful of you who still have not taken the test. So I strongly encourage you to get this figured out, because for those people who don't take their tests in a reasonable amount of time, they're going to end up getting a 0 for it. And I'm going to be recording one more video after this one, and then I'm going to record some videos for Chapter 8. And then I'm going to go on vacation, and I'm going to be out of town for about a week. Okay? I'll send an email out to everybody. Okay? So with that, have a good day, and I'll record another video here in a few minutes.